Hello, everybody. Welcome to Lecture 1 of STA 513. So STA 513, the Intermediate Linear Models portion of the course. What this looks to do is it looks to blow up what you guys learned last year, or if you're delayed a couple years, whenever you took the regression model course, STA 512, we look to build off of that model, off of that modeling structure, and to kind of pick up where you ended 512. And with 512, you ended things with regression modeling. And so one of the things I think we're going to look at is I'm going to give you guys with the screen share I'm going to go to what I call, you guys will see on D2L, topic 0. This topic 0, a friend of mine's at the University of Rochester, I think he might move to University of San Diego now, or San Diego State, Shin Tu, who was, we worked together at the University of Pennsylvania. He was on my PhD dissertation committee. And he teaches a similar course at Rochester on this topic. And he provided me this slide. Let me see if I can get to the full picture. I think this does a really nice job of showing you guys where we're going this year and really where this whole second year of the program focuses in on. Where you guys were last year was right here, focusing on the linear regression model. And when you got to the end of 512, you started talking about analysis of variance. These fall under the category of linear models. And what intermediate linear models looks at, it looks at really extending what you learned from ANOVA and ANCOVA and bulking it up. Bulking up with respect to model fit, model interpretation, and model diagnostics. What we will additionally talk about during this year is extensions of the linear models. And the two extensions of the linear models we're going to focus on when we start getting into November is this idea of random effects models, or sometimes they're referred to as mixed models. And this is where we have multiple sources of error. We'll see an introduction of that tonight in chapter 16. But we'll really extend the discussion on this when we get to chapter 25 of the book. So this is going to be the big thing that we focus on, really extending the ANOVA, the ANCOVA models to, again, like I said, model fit, model diagnostics, model interpretation, and then looking at extended models to the mixed effects models, but also this way as well. We also want to talk about repeated measures model. So the data you looked at 512 is sometimes referred to as cross-sectional data. You have one cut in time. One cut in time. You may have covariates that look at previous points of time, but you're looking at the outcome at a specific time. That's a cross-sectional cut. And in reality, a lot of the data I have that I work with looks at data over periods of time. You guys are going to talk about this one data set called the NIDA Cocaine Collaborative Treatment Study. It's 20 years old, but it was really my first foray into clinical data, and the database is so rich that it's a great illustration of the topics that we do in 513. That data consisted of 7 repeated measures, where we looked at people at baseline, what we called month 0. The intervention was applied over 6 months. We had monthly primary assessments at month 1, 2, 3, 4, 5, 6 to get to the end of treatment, and even extended to a follow-up. But basically, one of the big things we were interested in was looking at intervention effects over the repeated measures of time. When we start living in this world of repeated measures of time, we lose one of the big assumptions of the regression models you saw last week. That's independence. So when data is no longer independent, we have correlation. And we need to not ignore the correlation, we need to model it. And the repeated measures models look at modeling that correlation, or what we call that within subject or within unit correlation. So we're 513's gonna live in this area, the mixed model, well, the linear models, the mixed models, and the repeated measures model. Mixed models is just a model that includes random effects and may include other terms. And when we have those other terms, we should think of those other terms as fixed effects. And that creates the mixed effect model or the mixed model. Again, we'll go into full discussion of this in chapter 25, get a little introduction in chapter 16 tonight. But basically, this is where we're at. Where those of you guys who are taking 507, you're going to live in this area here, this generalized linear model. And with the generalized linear model, you're going to be exposed to contingency table discussion at the beginning of 507. You'll take that into logistic regression modeling, to log linear models and log linear tables. All these models fall under what we call not linear models, not general linear models, but what we call generalized linear models. And these generalized linear models can be extended to include random effects, which leads to a discussion in the longitudinal data analysis course called generalized linear mixed models. And a topic you'll see at the end of 507 called quasi-likelihood models, which fall under where one modeling paradigm called generalized estimating equations lives. So I think this gives kind of a really nice lay of the land of what you guys will see. We'll see this year in 513, as well as those of you guys taking 507. So I think that becomes, really a big component of what you guys will see this year. So that's what I call topic 0. What we want to talk about tonight is what I call topic 16, or really chapter 16 of the book. So let me get to that here. So this chapter 16, you're going to see 513, I break into parts. Part 1 is the one-way ANOVA model, one-way analysis variance model. And you were introduced to that in 512 last year. What we're going to also see is part 2, which will go into the terminology of the two-way ANOVA, which you may have been introduced to that briefly in 512, but we're going to again extend that. Part 3 is what we call the mixed effects models, or the, the analysis covariance, two-way ANOVA, three-way ANOVA, multi-way ANOVA, and then part 4 is the random effects mixed models, longitudinal data. So kind of 4 parts of 513. This is the beginning of part 1, which we call the single factor study, or the single factor ANOVA. So like a regression model, you have Y, the continuous outcome. But in this model, the predictor is a categorical predictor, not a continuous predictor. The regression model, when you guys ran the simple linear regression, it was a continuous X predicting a continuous Y. You may even float it around with a binary X predicting a continuous Y. When you got to the end of 512, that's when you start seeing the categorical X predicting the continuous Y. That's where we are. We have a categorical X predicting a continuous Y. When this factor variable is binary, that's where you go to the t-test, the independent sample t-test. Some people, the independent sample t-test and the ANOVA model run, pretty similar as well. They are basically the same. So, some people go, that's a t-test. Well, an ANOVA is a t-test. It's just where your factor has 2 levels. Usually when people talk about the ANOVA, though, it's usually when the predictor variable has multiple levels. So the study I was just telling you about with the cocaine addiction trial, now that one we were really worried about people using cocaine. So the measure outcome, one of the measures outcomes was days used cocaine the past month. So at the monthly assessments, we were quantifying their usage. So we could look at, say, month 3, and we're trying to see whether or not the interventions the patients were randomized to, how, which intervention's working best. In the cocaine trial, you're going to see this study consisted of 4 treatments. Patients randomized to individual drug counseling, group drug counseling, a form of psychotherapy called cognitive behavioral therapy, which we abbreviate CT, and a form of psychotherapy called supportive expressive or dynamic therapy, which we abbreviate SE. 4 levels. And what we're really interested in is whether or not there is an on average difference across the 4 levels. So again, the single factor can be an experimental factor-like treatment. In this Daruba study from 2005, we focused on depression and treating people suffering from major depression. These patients were randomized to 1 of 3 arms. Cognitive therapy, again, a psychotherapy. ADM stands for medication, and placebo, which is obviously, the medication, packaged like the medication, but it's no drug. It's what we call the control group. In this study, we were looking, okay, at the end of treatment, on average, which of the 3 treatments yielded better depression scores? So we have a categorical predictor, 3 levels, CT, ADM, placebo, predicting a continuous outcome, which happens to be a depression score. And, a lot of these psychological studies have scales that quantify a person's impairment. In this study, the 2 scales quantifying, impairment were the Beck Depression Index and the Hamilton Severity Rating of Depression Index. So in this case, the predictor is an experimental factor. That means patients are randomized to the 3 treatment arms. And again, the randomization is to create balance so that one treatment just doesn't have all the good guys, that the good, the bad, and the ugly, if you want to roll it that way, are kind of evened up across the respective levels of the factor, obviously to reduce bias. But the factor doesn't need to be a randomized component or what we call an experimental component. It could be an observational component. And in this Dave Atkins study, a colleague of mine, a good friend from University of Washington, he was really big in his area. He's a psychologist by trade, but he's super statistically savvy. But what his focus was in this one study was to look at this marital, I think it's called the Marital Severity Inventory. And what the Marital Severity Inventory, MSI, does, it quantifies basically how close the marriage is to dissolving. And so what they were looking at was, okay, over the course of therapy, how was the MSI? And the obvious thing was, you want the MSI to be at a, low likelihood scale of divorce. And so what his predictor was in this was, it was really the, they quantified the dominant member of the couple. So this term gender was the dominant member of the couple. So in this case here, the gender was, coded as, in this case, male for, male for a heterosexual couple, female for a heterosexual couple, and then they, linked it to, they want to also account for some of the same-sex couples as well. And so, and it'd be like, okay, the male's the dominant one of a same-sex couple of two men. Women were this, was the dominant member of the same-sex couple for two women. Obviously, with the same-sex couples, the gender, is linked right to the coupling formation. But in this case, we have 4 levels of gender. Male heterosexual couple, female heterosexual couple, male same-sex couple, female same-sex couple, and look to see if there's a difference there. One of the things that they were kind of really curious of was whether or not the couple composition, whether it was same-sex or a different sex, how that differed. So that was the origin of that. Obviously, in that case, the gender is not randomized; it's observed. So that becomes what we call an observational factor. For us, it doesn't really matter whether the factor is experimental or observational. We just have to go through the analysis approach. What you're going to see is the textbook examples we look at really focus on a lot of the observational results. When you guys deal with a lot of my examples, you're going to see most of my data come from a lot of randomized clinical trials data, and you guys are going to see, the same, the experimental factors, mainly treatment or randomization assignment or something like that, as being the key factor. Now, with the one-way ANOVA, when we talk about one-way ANOVA, again, remember ANOVA, analysis of variance. In this ANOVA model, analysis of variance model, the outcome Y is a continuous variable. You can call it the outcome or you can call it the response variable. The X variable or the predictor, sometimes it's called the covariate of interest, or sometimes it's called the explanatory variable. This is a categorical variable. We call this a factor variable. And again, I'm going to show you guys a lot of the stuff in SAS. You are free to use R, free to use STA, free to use SPSS, free to use whatever software you feel most comfortable in. I'm really good with SAS, with the data management, data organization, the graphics. I know a lot of you guys, taking the R course or currently taking the 1 credit course. I know a lot of you guys are really good with that. I don't care what you use, just as long as you're able to do the models and interpret them properly. For us, with the explanatory variable in SAS, we're going to see this goes in the class statement. Now, for the explanatory variables, the possible values, we call it the level. So this is nothing more than extending the independent 2-sample t-test to multiple levels. And again, if you're doing SAS, the independent sample t-test, proc t-test, the multiple level could be done in proc GLM, proc ANOVA, proc mix, proc GenMod, proc reg. We're going to focus on proc GLM. This is going to be, GLM stands for general linear model. This could do a lot of what we needed to do. Now, the ANOVA model and the regression model, they're not really different. They're not really different. Just they're different in the way the model's presented. You guys saw in the 512 class that if you had categorical predictors, to bring them to the model, you needed to create dummy variables, right? So if X is my categorical predictor, and if we go to the Darubas example, where I have 3 levels, treatment, medication, placebo, I would need 2 dummies to model that correctly, where I can let X1I be the dummy here, where again, this could be the indicator of the person receiving CT, that cognitive therapy. X2 could be the second dummy, indicating whether or not the person received medication. So if we're dealing with patients, we can see in this case here, okay, if a person's getting CT, this is 1, this is 0. If the person's receiving medication, this is 0, this is 1. If the person's receiving placebo, this is 0, this is 0. We'll never have the situation where both X1 and X2 are 1, right? Because the patients are assigned to one treatment, not multiple treatments. So therefore, they could not have both cognitive therapy and medication. So we got that. So again, our intercept, these represent deviations from the intercept for the respective level. Then EI is the error in the prediction for the ith individual. And that's the outcome for the ith individual. The ANOVA model, I kind of like this layout a little more because really what we're interested in is the mean per level. And so what you guys see here is this becomes double subscripts, IJ. So what this represents here, this is the jth person in the ith level of the factor. This represents the mean for the ith level. And then this is the error for the jth person in the ith level. This is what we call the cell mean model. When we fit the ANOVA, we're really fitting this model where we are interested in estimating the mean per level of the explanatory variable. We're fitting this. The algorithms you fit, SAS, STA, R, SPSS, are really fitting this model. So algorithmically, we may be talking about this model, but algorithmically, this model is being fit by the software. So the big difference between regression and ANOVA is in the regression model, the predictors are either continuous, quantitative, or binary. In the ANOVA, the predictor is categorical, or what we call qualitative. And what we're going to see is the regression model assumes what we call a linear relationship amongst the predictors on outcome. The ANOVA model makes no assumptions of the nature of the relationship. So while both models are doing the same thing that we just saw, the cell mean model, the ANOVA model, just says, hey, the means can have any kind of relationship, any kind of pattern. And the ANOVA model is embracing that. So the big thing is the nature of the relationship of the predictors on outcome imposed by the model is that the regression model assumes a linear relationship with the predictors, where the ANOVA assumes no assumptions. So now, when we go back to our regression models, right? With the regression models, you had assumptions about the model. And the big thing were the errors were normally distributed, right? You had this thing called, that the errors were, had homoskedasticity, which meant that the error variance was constant over the range of the predicted values. In the ANOVA model, that homoskedasticity assumption falls into what we call homogeneity of variance. That means the variance of the data within each level of the predictor is the same. That's that homogeneity of variance. And then independence of the data. So again, right now we're going to assume the data is IID. And then what we're going to see is the mean, the predicted outcome, depends on the level of the factor. So now with the regression model to the ANOVA model, one of the things we're going to see is not only are the errors normally distributed, but in the ANOVA model, the cell means are normally distributed. And we're going to see what that looks like. So again, we got the Y is the outcome variable. Let R be the number of levels, right? So in a lot of situations, the number of observations in each level can be unique. So you have as many as you want. With the cocaine study that you guys will see, 487 randomized patients across the forearms, and don't quote me on this, but I believe the numbers were 121 for CT, 124 for SE, 117 for IDC, or my fault, for individual drug counseling, and 119 for group drug counseling. So they weren't the same, so sometimes that's not the case. And a lot of studies that look, at later time points, usually they're not the same because of dropout. So we got that. So we got the number of observations per level. We got NT, the total sample size. And then we got YIJ, like we said, the jth observation in the ith group. So this is our basic model that we see there. So we got the error. The expected value of YIJ is the mean for that level. The variances are constant. That's that homogeneity of variance issue. The YIJs are normally distributed since the errors are normally distributed. The errors are independent. Then the big thing with the ANOVA model is that the observations within a level are normally distributed mu-I, the cell mean, and variance sigma squared. That variance sigma squared is the constant variance, the error variance across each level that we assume to be constant. From the regression model, when you guys were estimating variance, MSE was your estimate of sigma squared. In the ANOVA model, the MSE is the estimate of sigma squared as well. You guys may see the regression models in books, or if you're Googling around, on what we call this matrix model. And in this case, the bold represents the vector of outcomes. So if you have 20 patients, this is 20 by 1. Each row is an outcome for the 20 patients. X is sometimes what we'll call the design matrix. So now the design matrix, the form of the design matrix depends on the model you're fitting, right? So if you're fitting it through the regression model, you're going to see the design matrix look one way. If you're fitting it through the cell me model, the design matrix will look something else. And what the design matrix is each row of that matrix X corresponds to an individual, or what we call the unit of the data. The columns depend on the predictors in the model. And so, whether or not we're going with, the dummy variables, or whether or not we're going to the cell me model, is going to have an impact on that design matrix. The beta is the vector of regression coefficients. Even though we're fitting in a ANOVA model, we're going to get coefficients, and we're going to call them regression coefficients. And that's basically showing you the parameters being estimated by the model. So just like you saw with the regression. So getting predicted values, these coefficients are going to be pretty important. Then the epsilon is a vector of errors, that we start, that we'll see as well. So again, the rows of these matrices or vectors correspond to the unit. So the first row is the first patient. The 10th row corresponds to the 10th patient. If you have 25 patients, the 25th row, the 25th patient. So if we're fitting the cell me model, and say we're fitting the cell me model where, in this case, we have 6 patients, and every 2 patients is in one of the 3 arms. So we're dealing with the Darubas data. The first 2 go to CT. The second 2 go to ADM, and the third sets of 2 go to placebo. And so now our vector outcomes is, okay, the first entry, the first patient in treatment 1, the second patient in treatment 1, the first patient in treatment 2, the second patient in treatment 2, the first patient in treatment 3, and the second patient in treatment 3. So that's the rows. So now, in this case, the rows of the design matrix correspond to the 6 patients. But now the columns really correspond to what we're estimating. And with the cell mean model, we're estimating 3 parameters. Mu1, the cell mean for level 1 of the treatment variable. Mu2, the cell mean for treatment 2. And then mu3, the cell mean for treatment 3. So this design matrix, we're creating 0, 1 indicators indicating what column corresponds to each of the 6 patients, right? So in patient 1, we got 1, 0, 0. 1 because they're in treatment 1, 0 for not treatment 2, 0 not in treatment 3. Same thing for the second patient. For the third patient, they're in treatment 2, so they're not in treatment 1. Yes, treatment 2. No, treatment 3. The fourth patient, the same thing. The fifth patient, they're in treatment 3. So if we go across the rows for the fifth patient, are they in treatment 1? No. Are they in treatment 2? No. Are they in treatment 3? Yes. And the same thing for row 3. So we have that design matrix. The regression coefficients, these are the terms we're estimating in the model. And our goal in this cell mean model is to estimate the mean for level 1, the mean for level 2, and the mean for level 3. And then we have the respective errors for each patient. So the design matrix, the matrix representation of this structure, y equals xb plus epsilon, is right there. They're the components. So that becomes our, in essence, chore. When we start looking at the expected values, right, the expected values of the y's end up being xb, the regression coefficient or the errors get lost in the expectation. And so what you could see here is when we're trying to estimate the mean for person 1, it's this design matrix multiplied by that vector. So again, if you think about the matrix algebra for the first, first row, patient 1 in level 1, it's this first row times this column. So it's 1 times mu1 plus 0 times mu2 plus 0 times mu3. That's mu1. Similarly with the fifth patient, 0 times mu1 plus 0 times mu2 plus 1 times mu3, and that's mu3. So that's the way the matrix algebra is working. We're going to let the software do the matrix algebra for us. We're going to have to keep in mind some of the components of it, because some of the things that we have to bulk up, like estimate statements, like contrast statements, they kind of work, with the matrix algebra in kind of the background. So, we have to be aware of the matrix algebra. Don't beware of the matrix algebra. We have to be aware of the matrix algebra when we start doing those estimates and contrast statements. And then one thing you're going to see is the variance of the error is going to have this form here, and down the columns, the variance for person 1, the variance for person 2, the variance for person 3, all the way down to the variance for person 6. We assume a constant variance. That's that constant variance, homogeneity of variance assumption we got. And in this case here, we're going to estimate that parameter. And our estimate of that sigma squared is the MSE, the mean squared error, just like you saw in the regression model. Matrix algebra-wise, the sigma squared y, sometimes we're bringing sigma squared times the identity matrix. So the identity matrix, just remember that's the matrix, just one down the main diagonal. So, you know, when we're estimating the mean level, the means for the levels with a pooled variance, that pooled variance is just like the regression model, and that's our MSE. Now, that's what the MSE is. You're going to see the book makes two big distinctions in models. The one model we call the fixed effects model, or the ANOVA model 1, and the second one's called the random effects model, ANOVA model 2. So the combination of the two creates what we call a mixed effects model. And you know, that's what the book will refer to as a mixed model. We'll see the random and mixed effect model in chapter 25 and 27. For what we do from chapter 16 to chapter 24, we're living in the fixed effects world, or what the book refers to as ANOVA 1. I'll give you a little flavor of the ANOVA 2s within chapter 16, even some of the other chapters, but we'll really get into the full modeling structure of this random effects component in chapter 25 and chapter 27. And when we do that, we have to leave, you know, SAS-wise proc GLM to what I call, you know, what we call proc mixed in SAS. And so that proc mix is going to be a big component of what we need to do as we start moving on, you know, as we start getting down the road a little later on, you know, in the course. Quick example of a random effects model, just to plant the seed for you guys as we start getting down the road, is what we're going to see is the unit of data, the thing that's giving you data, you know, the unit. And the textbook example is they truly are units. For me, the unit is a patient. You know, in a lot of the data I work with, again, a lot of the psychological and medical studies, I'm dealing with patients. And the unit is who's giving you the data. And the big thing is we hope that the units were randomly acquired. You know, an experimental factor, not only that, they're randomly assigned. Random means you have some error. And when you have some error, we model that. We need a model, and we're modeling through the MSE, the mean squared error. So while we have patients randomly assigned, what if we have another component that has randomness associated with it? In this Kristoff study from 2004, this again was looking at, you know, substance abuse, but was looking at patients randomly assigned to treatment arms. But those patients were randomly assigned to randomly chosen therapists, right? So now we have two levels of randomness. The randomly chosen patients being treated by randomly chosen therapists. Whenever you have any sources of randomness, there are sources of variance. And those sources of variance have to be modeled in, you know, in the modeling structure. They have to be accounted for in the modeling structure. Well, you know, the GLM model we have there is always accounting, and even the regression models always account for the randomness at the unit level, at the patient level. When we have another source of randomness, we need to accommodate that. And how we accommodate that is through random effects models. So with the therapist being chosen randomly and not fixed, then they are a source of variance that we have to model. Now, suppose this. I got these randomly chosen patients chosen by these 6 therapists. And these are the only 6 therapists, you know, to be that meet the qualifications to treat this kind of patient. So a fixed effect variable means you have a representation of all the possible levels. A random effects model means you don't. You got a random sample of all the possible levels of that variable. So this becomes a really tricky analytical component that we have to accommodate for. So a lot of times when you guys are out there, people go, well, I got this thing. Should I treat it as a random effect or fixed effect? This requires a lot of discussion by you with the investigator. I'm gonna call whoever's giving you data, I'm gonna call them the investigator if it's their data and this data you're analyzing. And with stat, the big thing with stat to remember, it's a field of communication, not mathematics. It works in mathematics, but it's communication. And communication is a lot of us explaining the models, interpreting the models in a way that is understandable. But communication is also us asking the right questions and listening to the response to make sure we're getting the sufficient answers to our questions, right? So when you're dealing with something and people go, I don't know, is this a random effect? The big thing is whether or not, and we're going to talk about this more in chapter 25, but whether or not you have all the possible levels. And if you have a subset, that sounds like it's a random effect. You have a random number of levels from all the possible levels. So in this case, with the therapist being chosen randomly, I have to model that variance. If we don't model that variance, the variance of our model is underestimated. If the variance of our model is underestimated, that means our standard errors are underestimated. If our standard errors are underestimated, that means our test statistics are bigger than they should be. Which means if the test statistics are bigger than they should be, that means our p-values are smaller than they should be. That means we're more likely to make a type 1 error because we're underestimating the variance. We're more likely to falsely reject a true null, right? We don't want to do that, right? You don't want to do that. We want our predictions, our inferences to be correct, right? So anytime you're ignoring variances, sources of variability, this could lead to an underestimation of the model. Now, sometimes, the sources of variability, where they go, we're going to see this is a little complicated in chapter 25, but basically, you have to model the data, right? Not throw data in the model. And unfortunately, I know 512, 507, 513, you see this semester, we're giving you guys a bunch of different models, right? And the way a lot of the classes have worked and work is, here's this, let's use this. Here's that, let's use that, right? When you get out there in the real world, you have to choose the model to use, right? And it's not like, okay, discussion, topic, discussion, example, you do. That's a lot of the structure of what you guys go through academically. But when you get out there, you have to choose the model. And the biggest thing we got to do as statisticians is model the data. Not throw the data in the model, but model the data correctly. And that's the biggest leap you have to do to become a statistician. Is, okay, how do I choose the right model? And how do I choose the right model? Not in an academic setting, out there in the real world. And that's where you learn the most, right? So when you guys are done with the program or whatever, your education's not done. My education's not done. Now, there's new modeling paradigms, new software, right? I've been SAS guy forever, but I've gotten more, in depth with R over the past decade. You guys with data management, I've done R more for analytical packages, You know, you guys can probably do a lot more of the graphing and the you know, and the data management component of R better than me. But you know, I'm still learning. Right? I'm still learning. You know, some of these packages, some of their limitations. I'm learning different modeling structures. Education never stops, right? No, it's like success. Success isn't a destination; it's a continuing road, right? And you guys are in this program to travel further down that road and keep traveling, right? And you know, my job is to help you, and yeah, and that's what we're here for, is to get that. Give you guys the first example. This page 685, 686, the textbook. Let me jump there real quick to the textbook, just to get you guys there. If I go really quick to the to the textbook. I go to chapter 16. So page 685, 686, I believe it was. Okay, so here's the first example that you guys will see here. Maybe a little bigger. Get rid of, maybe it's a tad smaller. So in this case here, we got this Kenton Food Company wishes to test 4 different package designs. So this is observational, not experimental in some sense. Well, I guess depending on how they assign it, for a new breakfast cereal. So they choose 20 stores that have equal sale volumes, right? So again, the stores are basically comparable, right? So we're not looking at sales volumes as a possible confounder. Again, throwing out some terminology guys were exposed to last year. So the stores are the unit. Each store is randomly assigned one of the packages, so it is a random experiment. So package is experimental factor with each package design assigned to 5 stores. A fire occurred in one store during this study period, so this store had to be dropped from the study. Hence, one of the designs was tested in only 4 stores. Stores were chosen due to comparable location and sales. Other relevant conditions could affect sales, such as price, amount, location, and shelf space. And special promotions were kept the same for all the stores in experiment. Sales in number of cases, that's the Y, were observed for this study period and recorded. They're in table 16.1. This study is a completely randomized design with package design as the single 4-level factor. So what we want to do is we want to make the inference about the equality of the cell means across the 4 levels. Here's a picture of the graph, and then here's the data. So at design 3, store 5 is the one at the fire. So we lost that data. Gives us a little picture right there. Basically a scatter plot. Now, with the regression models, the scatter plots were pretty useful because they could show you, give you a sense of the regression, strength. In this one, remember, the predictor is a category. So it's not really so much, whether or not we're looking for a linear relationship. In fact, in this one, it looks like we might have a slight decrease followed by a respective increase that we're dealing with. But that becomes, kind of where we're at with this component here. So now I'm going to jump you guys to SAS real quick. So I'm in SAS, right? You guys see I got these number on here. If you don't see the number on, if you go to this white box right there and type number on, that will go on. If you don't want them on, type number off. They're gone. When you guys open up SAS in the enhanced editor, it should look like that. I want to turn them on just so that we're keeping together. Here's the data. right? So, the data I got there, I just copied from the data file in the book. Again, as you guys saw, with the first class, or as you guys see when we go over the syllabus, the materials on the materials on D2L, you'll see this information there. I'm gonna load this data, right? So the Y is the variable cases, the design is the level of the factor, and then store is counting the observation within each level, right? So you can think of design as the I in the notation, and the store as the J in the notation. Let's go ahead and load the data. So 19 observations. Again, we got the one lost store. I'm going to go ahead and print the data. And there's the data printed. Okay, what we're going to do now is let's fit the ANOVA model, right? So now with the ANOVA model, right? So if we're thinking about the ANOVA model, we go right here and we go to the ANOVA model here. Remember in this case, oops. We go in this case, our null hypothesis ends up becoming this. So our null hypothesis becomes that the equality of the four cell means, right? So in this case here, the regression model, no association. So in essence, no association of the categorical factor variable on outcome is the equality of the four cell means. Is the equality of the four cell means. That's just what we're doing right here. Well, if you guys go back to 506, right? You may have looked at this when you were in the hypothesis testing component, the equality of the two cell means. And you may have went, okay, we can create the test statistic, which T hat is X bar 1 minus X bar 2 over the square root of SP, the pooled standard deviation times the square root of 1 over N1 plus 1 over N2, and then minus, the claim difference, which is usually 0. But, that became your guy's T hat. Well, now we got the four means. We could mimic the same approach. Go, okay, let's look at this. Let's look at mu1 compared to mu3, mu1 compared to mu4, mu2 compared to mu3, mu3 compared to mu4. If we do that, that's basically 4 levels of the group, choosing 2 of them at a time to create a pairwise comparison, independent sample pair comparison. 4 choose 2, 6. That's 6 comparisons for one test. That's 6 tests for one null. Well, that's not efficient. We need one model to test the equality of those 4 means, right? This is the one-way analysis of variance. Now remember, that's the null. I thought that would stick with this. My fault. I keep hitting the thing. This is the alternative. Not that they're all unequal. It's at least one is different, if I could tell you. at least one is different from the pack. At least one separating from the others. No, so it's not that they're all unequal. It's that at least one separating. So they're all equal. The opposite is not they're all unequal. It's just at least one separating. So that's what we got there. And, you know, so that's what we're looking at here. So now, well, let's just cut to the chase and say, how do we model this in SAS? How do we model this in SAS? Well, to model this in SAS, this is what we're going to do. It's proc GOM. You know, so just like any proc you saw in SAS before, I'm telling SAS the data set I'm working on, which is the Kent data set. Line 45 is the class statement. The class statement is where you put the categorical predictor. In this model, design is the categorical predictor. I'm telling SAS it's categorical by putting it on the class line. So now here comes my model. Y, that's my Y, cases equal to my predictors. I have only one predictor, that's design. The slash solution, remember the stuff in blue is options. The slash solution is I'm asking SAS to produce the regression coefficients. Line 47. I'm asking SAS on that means line to give me the estimated cell means for the 4 levels of design. Now that HOV test, right? HOV test. What do you think it abbreviates for? Now, HOV test. Now, HOV test is not high occupancy vehicle test. HOV test is homogeneity of variance test, right? So it's actually going to test whether or not the variances across the 4 cells are equal. You know, so in this homogeneity of variance test, remember, homogeneity, like homoscedasticity, one of the assumptions of the model. For us, the homogeneity of variance test is also has a null. So in this case here, the homogeneity of variance, let me go ahead and go this way, more symbols. Jump down to the so if I drop down real quick, just trying to get the Greek symbol. Where are you, Sigma? There you are. Right, so in this case here, you get sigma squared. All right, so the homogeneity of variance is looking at this null. All right, so if we focus on this, this is the homogeneity of variance test. That's the test of the cell means, or basically the ANOVA test. So the homogeneity of variance test is looking at this. Now, assuming the 4 variances are equal and the alternatives, at least one's different. This is one of our diagnostics, right? Does the data fail homogeneity of variance? Well, the big question is, well, what do we do when we fail homogeneity of variance? We'll see this in, in some, I guess, chapter 18, we really get into the model diagnostics. So chapter 16, we're building the model. Chapter 17, we're bulking up some of the additional things we do within the model. Chapter 18, we go through some of the model diagnostics. That's part 1 of intermediate linear models. So we got that right there. So that is what this is testing that null. So let's go ahead and run it. Let's go ahead and run the model real quick. So again, procGLM just calls the ANOVA model. Data equals Kenton, the name of the data set, our categorical predictor. In the class statement, our model statement, the means to get the cell means, and then we quit the procedure. So when we run this, here comes SAS. So here comes the output. Right, so here's the beginning of the output. So now the first box, SAS is showing me the levels of the categorical predictor. And you can see in this case here, I have 4 levels corresponding to the 4 types of designs. This area here is pretty important, especially when you guys start dealing with real life data. Real life data has a lot of missing values. And so, you got to be a little aware of, how much data are you losing due to missing outcomes or missing predictors. But 19 data read, 19 used for the analysis. So I really try to pay attention to this in my modeling. Like if there's a big drop off, a lot of times I have to say to the investigator, well, why do we lose so many? Now, this here lets me highlight it. This is testing the null for the one-way ANOVA model. So this box here is doing testing this null. So in this case here, if we go back to SAS, that is testing that null there, right? So what you guys see in this case is this F value is my test statistic. And there is the p-value, right? So again, I know there's been a lot of talk about, p-values and a lot of things trying to move away from p-values, but they're still the index we still use. And so what you guys could see is we got an F value of 18.59 and a p-value well below the alpha level. Let's just assume the alpha level is 0.05. So what this is saying to me is based on the available data, I have sufficient evidence in my data indicate that the cell means are not equal. That in fact, at least one is significantly different than the rest. One is significantly separating from the rest, right? So I'll say again, based on the available data, right? We have sufficient evidence in our data indicate that the means are not the same, that we can reject that null of equality of the cell means in favor of the alternative that at least one is significantly separating from the rest, right? That's highly significant, right? So that becomes our F and the p-value. You could still get indexes like guys saw in the regression model, the R squared, basically the percent of variance explained in the outcome by the ANOVA model. Type 1 sums of squares, F and p-value. Type 3 sums of squares, F and p-value. For the one-way ANOVA model in chapter 16, 17, 18 doesn't really make that much of an impact. When we get beyond that, the type 1, type 3 sums of squares do make a difference. In 512, you may have been exposed to it. the type 1 sums of squares are usually that order sequence sum of squares. So it's showing you the significance of the predictor controlling for the predictors that preceded it. Well, it's only one predictor, so nothing there. And then the type 3 sum squares are the significance of predictor adjusted for all the predictors in the model. And yeah, that's there. So if you notice, all 3 of these are the same. So for the one-way ANOVA, it doesn't matter which of the 3 you use. When we get down the road, we're going to lean more on this as the type 3 sum squares as our test of significance. But that's what we got. So now, basically say, hey, enough evidence, the means aren't equal, at least one's different. In this, it's not like, it's not like, like a TV cliffhanger. Hey, at least one's different. Catch you later, right? Or or whatever. It's kind of like like who knows when the next season of TV is coming back. So like those you guys have shows that ended on cliffhangers. You're expecting some of them come back in September, October. Who knows? When they plan to come back. But basically, you've been hanging on the edge of your seat. Especially in light of some of this stuff that's going on. Waiting for, whatever chaos going on in your life, waiting for that to come back to resolve, did this person survive? Did they get married? This person get killed? This person coming back? Whatever kind of TV you're watching, you're kind of looking at that stuff, waiting for that to come back. Well, for us, our analyses can't be cliffhangers. Our analyses have to, explain the story. We have to give a full story. We tell a full story. So for us, we just can't say at least one's different. The investigator is going to want to know, well, which one's different or which ones are different. Well, one thing that can help is this box, right? In essence, when SAS, R, or whatever you're using are finished model, they're basically using the regression modeling layout. And with the regression modeling layout, it'll create dummies. In this case, it's 3 dummies that we have for the 4 levels. And in the regression models, there's always this thing we call the reference group. SAS puts the reference group at the highest level of the categorical predictor. So in this case here, as you guys see here, design 4 is the reference level. So the intercept you see here, the intercept you guys see here is the on average estimated mean for the reference cell. So this model says on average 27.2 cases are sold of the product with design 4. These show you how much each of the other 3 designs differ from the reference cell. So what you guys can see is that design 1 has on average 12.6 less cases sold than design 4. So again, if you're doing the math in your head, you could say here, that's 12.6 cases sold less. So on average, design 4 sells 14.6 cases on average for a given period. If we go to the next one, this minus 13.8, this is saying to us that design 2 on average sells 13.8 cases less than design 4. So again, if you're doing that math in your head, that means design 2 sells on average 13.4 cases per month. So now we go to design 3. And what you see with design 3, as we do this, design 3 sells 7.7 cases less than design 4. So again, the minus signs are giving you the direction. And if you do that math in your head, that means design 3 sells on average 19.5 cases sold, per month. So again, keep those numbers we did in our head. Design 4, 27.2. Design 1, 14.6. Design 2, 13.4. Design 3, 19.5. So if we go back to our Word document, we can go, okay, let me get back here. So again, if I just label this out, so we got 14.6, 13.4, we got 19.5, and we got 27.2. So at least one's differing. Well, eyeballing the number wise, design 4 is the best. Now that on average results in the most cases sold. Design 3 is coming in second place basically at 19.5. And then we see design 1 and 2 are basically similar. Design 1 a little better, but it's really design 4 separates. Design 3 looks like it separates from the other two. They've got those other two together. So really what we say visually, looking at these numbers, that the separation's really being driven by design 4. That gives us the estimate and then the standard errors, right? The standard errors are the errors for the estimate. So the 1.45 is the error in the estimated mean for design 4. 2.05 is the error for, not for the estimated mean of design 1, for the estimated difference between design 1 and design 4. The estimated difference for design 1 to design 4, or design 2 to design 4, and the estimated error in the difference between design 3 and design 4. This box, the t-value and the p-value give us a lot of information as well. This t-value, this is testing whether or not this estimate is significantly different than 0. So you see it's 18.73, it's way off. Yeah. This one might not mean something. It's really saying, okay, hey, does design 4 have, in essence, have sales, right? And we could say, yeah, based on the available data, we're sufficiently, we're sufficiently confident that on average, the sales for design 4 are significantly different than 0, right? And in this case, we're thinking positive. Even though every test we're doing is two-sided, we're thinking, okay, sales, yeah. What's the store doing? Taking back product? No. We're thinking they are significantly selling product, is what that's saying. These 3 are the big ones. This one here is testing whether or not the difference, this delta, the difference between design 1 and design 4 is significantly different than 0, right? And so on this one, this is pretty good because this can help us tell the story. So we could see that design 1 is significantly separating from, design 4 is significantly superior to design 1. That's what this test is doing. If we go here, it's kind of the same thing. We see that that's estimating whether or not the difference between design 2 and design 4 are significantly different. And we see, yeah, they are significantly different. The design 2 is significantly, the difference between design 2 and design 4 is significantly different than 0. And then we see the same thing for design 3. that is well is significantly different than 0. So that is pretty important for us to get those two things across. And then we see the same thing for design 3. So what we've shown in this table here is that design 3, design 4 is significantly superior to the other 3 designs with respect to sales. So what's driving this overall significant ANOVA effect is that the fact that design 4 is significantly superior than the other 3. That's part of the story. Now, this is going to give us a box plot. Procter will give us a nice box plot of, of the data. Right? Now, one of the things that we got to think about is we're analyzing means. Why is this called analysis of variance? So when we're analyzing means, whether or not means are different, we call this analysis of variance. And what this really is like we talked about before, we can't really do 6 individual tests of the means, of the 6 pairwise comparisons of the means. We need one omnibus test. And the one omnibus test we have is really looking at the means, right? So if you guys look here, in the box plot, the diamonds represent the means. Represent the means. With analysis of variance, we can quantify the variability between these 4 means. If the variance of those 4 means is 0, that means all 4 means are the same. That's this null. So the variability of the cell means is 0, then there's no way we reject this null. The means are all the same, right? So that's where we're at. So with the analysis of variance, we're really looking at how much is the variance of these 4 cell means. And again, these are the 4 estimated cell means because we've got to estimate it through data. So how much variability is there of those 4 cell means? Well, the SAS output's given that to us. That's this row here, right? We have 4 cell means. So we're figuring out the variance of those 4, I won't call them data points, 4 data points. Remember, when we're estimating variance, we lose a degree of freedom. That's right there. We lose that degree of freedom. And with that degree of freedom, we're able to quantify that and able to get that we're able to quantify that variance, and that variance depends on sums of squares. You guys remember the sums of squared deviations that you guys did back in 505, and then this is the estimate of the variability across the cell means. That's 196.07. That variance across cell means, that's one variance. Whether or not that's big or not, we don't know. Everything depends on a scale, right? Everything depends on a scale. 196, is that a lot? $196,000? Yeah, that's a lot. $196? Yeah, that's a lot. Yeah. 196 pennies? $1.96? I don't know if that's a lot. You're just making a lot of noise when you walk. Ching, 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 ching. But hey, whether or not it's big, all depends on a scale. All depends on a scale. How we quantify this now is within each level, we calculate the variance within. How much variability is there within level 1, within level 2, within level 3, within level 4? So to create that variance, now think about this too. We have 19 data points, right? We're creating 4, within variance. The diamonds, they're between level variance. This one, we're calculating within level variance. So we got the 19 data points, 4 groupings. That's where we get the 15 degrees of freedom there. So the degrees of freedom of the error, and that's what we're using to quantify the within variability, is the number of data points minus the number of levels of the predictor. So 19 minus 4 gets us to 15. And then this becomes the sum of squares of the errors within the levels. And then the sums of squares divided by the degrees of freedom gives us a 10.54. So the sums of squares divided by the degrees of freedom gives us that. So this is the mean square between. This is the mean square within, or what we call the mean squared error. That's the MSE, mean squared error. So now we have a variance estimate for between, the variance estimate within. If you guys remember in 506, when you're introduced to the F random variable, the F random variable was used to assess variance, namely equality of variance. The ratio of those two mean squares becomes our test statistic of the F. And now we're looking to see whether or not those variances are significantly different, right? So the F values using this F. This F has a distribution. It's distributed F with numerator degrees of freedom 3, denominator is degrees of freedom 15. And then with this F, this is where we get the p-value. If that F value is 1, that means 2 ratios are equal. So you have equal variance within between. Right? So now for the ANOVA model, for us to reject the null, we need the variance between the means to be not bigger than the variance within, much bigger than the variance within. And that's where the F value and the p-value is going to tell us whether or not the ratio of those two variances are much bigger, whether or not the variance between the means is much bigger than the variance within. And if it's much big enough, determined by the p-value, that's where we have enough evidence to reject the null in favor of the alternative. So that really becomes what we're after. So the analysis of variance, the name, is really the way to get the omnibus test of the equality of the variance. I drop down in the output. This is doing the equality, is doing our test for homogeneity of variance. We're going to see in chapter 18, there's a lot of different tests. The Levine test is the default. And the Levine's test is the test that we're going to want to use, because that test, is, the one that is best apt to the ANOVA model. I'll talk about the other ones when we get to chapter 18, but we really want to use the Levine's test. And now the Levine test is assessing that equality of variance. This too is an F that you see right there in the p-value. Now, unlike the ANOVA model, now the ANOVA model with the null, now we're probably interested that one's better than the other. So in reality, when we go into the ANOVA model, we really are looking to reject that null. The homogeneity variance is the opposite. In this one, we don't want to reject the null, right? Because if the variances are unequal, then the ANOVA model we're fitting is violated. And if the ANOVA model we're fitting is violated, that means the inference based on using that model is flawed. Whether it's a good story or a bad story, it doesn't matter. It's just that the inference is flawed because the model is not correct, right? So when we're fitting models, the model assumptions are there. If the assumptions are violated, you can't interpret based off that model. You're interpreting off of a bad model. So again, this is where, a lot of people can run analyses. A lot of people can do basic things. What we need to do as statisticians is we need to tell the story of the data. And we need to tell the story of the data honestly and representatively. And that's our job as statisticians, is to be able to do that. So we really, in reality, we don't want to reject that null for the equality of the variance. So if we move back to the slides, back to the status output rather, you can see there's the p-value. So now the way I interpret this, based on the available data, we do not have sufficient evidence in our data to indicate the variances are unequal. This is the big line now. Therefore, we will assume equal variance across the levels. Therefore, no violation of the homogeneity of variance assumption. In reality, what are we doing? In reality, what we're doing is we're, in essence, accepting the null, right? Which again, in 505, 506, we talk about not accepting the null, right? We don't accept the null. In this case, with some of the model diagnostics, what we're looking for is, for us to say there's an issue, that issue has got to hit us like a sledgehammer, right? So for us to be worried about violation of homogeneity of variance, this has got to be significant, right? So, again, when we start talking about the models, we go, we assumed that there was no violation of homogeneity of variance in the data. We did not see any evidence in our data as assessed through the Levine's test of homogeneity of variance. But, you're just being honest with the person that you're explaining the data to, right? So again, unless this is significant, we're going to say, okay, we did not find any evidence of violation of homogeneity of variance. Therefore, we will assume the homogeneity variance assumption of the model is met and proceed with further interpretation based off this model. So it's kind of what we got. The graph plots again because I asked the means line. The means line, right? So this homogeneity of variance output, this plot, and this box are all being generated by line 47 now. By line 47. Now, we were doing the math in our heads, but that means line gives us the estimated means per cell and the standard, that's the raw standard deviation in the cell. This information here, the standard deviation, can be real useful with a violation of homogeneity of variance, right? The variances aren't equal. It may say to you, whoa, 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 whoa. In this case, we see a little bit more variability in group 4. Now, sometimes you got to keep in mind the data you're working with too. 27.2 is the highest cell, right? And so they have more room for variability. Like group 2, surprisingly, is second biggest. Sometimes the variability is limited depending on whether or not the level is hitting the floor or a ceiling. So you have to keep this in mind sometimes when you run into issues with violation of homogeneity of variance. But that gave us the cell means. Well, that was good. And again, if I run it really quick again, This box here really told us that group 4 significantly separated from the other 3. So say we go back and we go back to the investigator and we're saying, well, no, we looked at the data and we see, yeah, on average, there is a significant effect due to the design. Our data showed a significantly superior cases sold for design 4. And the investigator, the product manufacturer, whoever it is, like, well, that's great, but design 4 is out. Now, it's too costly to make. The packaging requires this, that, the other thing. We can't do design 4. What does your analysis say about the other ones? Well, you know, everything was compared to design 4. Well, one way around this is in SAS, we can use proc format to change the reference group, right? So if you guys see here, let's make group 2 the reference group first, and we'll do it for all 3. But I got proc format. I'm creating a value TXX format. So 1's GP1, 2's ref group, 3's GP3, 4's GP4. Watch the output when I run this. And notice line 66, I throw the format command, right? So again, you guys saw proc formats in 5.11. They're really nice tools to pretty up reports, pretty up graphs, but it's a nice tool here at this beginning stage. We're going to find a smoother way to do this, but a beginning tool here to figure out comparisons to each of the levels. When I go here and run this, here's the group levels. Now realize the ordering of the values is, if it's numeric, it's in smallest to biggest number ordering. That's why 4 was the reference group the last time. If it's characters or formatted values, it does it alphabetically, right? So I think, it alphabetically goes A to Z and then 0 to 9 if your format starts with a number. So for us, alphabetically, GP1, GP3, GP4, ref, R is last alphabetically. Group 4, group 3, my fault, group 2 is now the reference group. This doesn't change, right? Again, that was the overall ANOVA. We were using this box to dissect which groups were separated from the others. So now, the 13.4, the intercept, that was our estimated sales for group 3, which is, group 2, which is the reference group here. So group 1 has 1.2 more cases sold than group 3 or group 2. Group 3 is 6.1 more, and group 4 is 13.8 more than the reference group. And what we see here is group 1 and group 2. So based on the available data, we do not have sufficient evidence to indicate a significant difference in sales between group 1 and group 2. We're not saying they're equal. We just said based on the available data, we don't have enough evidence to say that they're different. Here, this is group 3 to group 2. And we see based on available data, group 3 is significantly different than group 2. So if you guys remember, the last one showed us that group 4 was significantly different to the other 3. Right now, we know group 3 is significantly different than group 2. Right? Remember, the product manager, the investigator says, hey, group 4 is out. What's your data say about the rest? Well, right now, we know group 3 is significantly superior to group 2. we don't know the group 3 to group 1 comparison. Well, we can mimic what we just did and try it again. If we do that again, I'm going to create a new format, right? Where now I make group 3 the reference group. And I use line 83 to get after that. So when I do this, check this out. So here we go. So with the box output, group 1, group 2, group 4, group 3 is now the reference group. Again, this doesn't change, but what we say here, 19.5 is sales for group 3. Group 1 is 4.9 units below group 3 and is significantly inferior to group 3. Design 3, if we will. Group 2 is 6.1 units below group 3 and is statistically significantly inferior to group 3. And then group 4 is 7.7 units larger than group 3, and it is significantly superior in group 3. But we answered the big question for the product manager. While group 4 was significantly superior to the rest, we see now group 3 is statistically significantly superior to the other 2, or the remaining 2. So again, we could say, hey, when looking at our data, while we saw group 4, design 4 was on average statistically superior to the remaining 3, looking at design 3, which had the second best packages sold, we see that design 3 is statistically significantly superior to both design 1 and design 2. Now, if the person goes, well, design 3's out, so we got a choice. I'm going back to what we just did before, where design 2 was the reference. We have a choice between design 1 and design 2. Let me tell you one thing though. Design 2 was our original design. The design 1, that's a new design with a little bit more color, a little bit more pizzazz. Now, how's that look? Well, here, this showed us design 1 compared to design 2. And while it's a 1.2 cases sold more, on average, it is not statistically significantly superior to design 2. So then we could say to the investor, well, if you look at design 1, design 2, while the new design with the more colors, has a little larger, gain in case sold, it is not a significantly improved gain and fit to warrant the new design, based on the available data. So based on the available data, we do not have sufficient evidence to indicate a significant increase, impact on sales for design 1 compared to design 2. That's the whole story. It's a long story. It's a lot of story. I mean, we just spent, 45 minutes going through this story. It's a lot. It's a big story. And it was a big story that we were trying to focus in on for the investigator. So that's pretty good. Now, let me show you something really quick in SAS. And again, there's a couple of different ways to do it in SAS, a couple of different ways to do it in R Studio, but I'm going to show you one of the plots I like in this and kind of mimics a little of the book. Here's the Kenton data, right? So the 19 rows of data. Here, I'm creating the averages by the 4 designs. So these are my cell means, which are the means we estimated. The 14.6, 13.4, 19.5, 27.2. Now, if you see here, I can print the data again. What I would like to do is to get this 14.6 on every row of the data where I've designed one. Do the same thing for the 13.4 for design 2. The same thing for the 19.5 for design 3 and 27.2 for design 4. One way I like to do this data merge in SAS, and again, you guys are exposed to a lot of data merge, data combinations, concatenations, all of that in 5.11. The one way I like to do it is through this procedure procSQL. And procSQL create tables K3. Go and create a new data set K3. And K3, this A dot, select A dot star, comma B dot star. This is telling SAS I want all the variables from both data sets, my first and my second. My first data set is the raw data, 19 rows of data, Kenton. I give it this little nickname A. Left join. So basically at the Kenton data set, I'm going to tag from the right the K2 data set with the cell means. So I'm joining K2. The Kenton's on the left. K2's coming from the left, joining into the Kenton data set. B's the nickname shortcut for the K2 data set. Now I'm going to do this join where the design variable in the A data set, Kenton, is equal to design variable in the B data set, K2. When I do this, this gets the average cases for each of the cells. So when I do this, I can create this plot first. That's basically connecting the cell means that you guys see there. Or the cell means that you guys see there. Now, with the ANOVA model, if the null's met, this connected line should be horizontal. It definitely isn't. Yeah. Now, the axis might change around, but that's kind of gives you kind of the sense of the pattern. Not a linear pattern like you think with a regression model. So that's that linearity assumption. These are the raw data. Group 1, Group 2, the reference group, Group 3. I guess I still have the format listed. So that's the raw data that you guys see in the textbook right there. But I think one of the better ones is this one, where I overlay the mean profile, the lines of mean profile with the raw data. And I think the beauty of this one is it shows the data. It shows basically the spread within as well as the cells between. So namely, I can get a sense of the variability within and the variability between. So that's pretty cool. That's pretty cool. I'm going to jump back to the PowerPoint slides, but not that PowerPoint slide, this PowerPoint slide. So we went through all of the modeling, loading the raw data, getting a sense of the notation, the cell mean model. We're estimating the cell means, the pooled variance. So the cell means that we see estimated, they're nothing more than the sum of the data within a level divided by the number of observations. Just within a level, add them up, divide how many you got. The variance per level is nothing more than we're going to do the degrees of freedom when we combine across the 4 variances, or 4 levels, my fault. So that's the variance within level 1. And then the pooled variance, this is where the degrees of freedom comes in. It's basically the sum of those deviations divided by n2 minus r. So that's all the mathematics that SAS, R, STA is doing for us. And, the cell means sometimes notated this way. So yi dot bar means I want the average of the data, of all the data in cell I. Y dot dot is the sum of all the data. Y dot dot bar is the total average, which can also be represented this way. And then, GLM basically is run the model through the least squares. And through the least squares method that you guys learned in 512, it really looks to minimize that, right? To minimize that component. Well, for us in the likelihood function, when you guys looked at 506, when you talk about maximum likelihood estimation, it really is getting to, minimizing this becomes where that first derivative is equal to 0. And that corresponds to the least squares approach. Again, the proc GLM code we saw before. Plot of the cell means. And then here's the raw with colors in this one. But again, the plot we just did in SAS is really good because it shows you the raw data and the cell and the mean profile line. Right? So when I'm looking at this plot, and one of the big things when I know we just jumped into the proc jump, but one of the big things we want you to have of is eyeballing the data, looking at the data to get some sense of what's going to happen. When we look at this data like this, okay, looking at that green line, I get a sense that I'm going to reject the null of the equality of the means. Looking at the balance of the dots around the mean profile line, none of them jump out as being really dramatically different variants compared to the other levels. This one, bigger. This one, smaller, but I don't think it's anything dramatic. So I'm not expecting to reject the null with respect to the equality of the variance. So the ANOVA assumption, I think I'm going to reject. The Levine's test of homogeneity variance, I don't think I'm going to reject. So again, when we're looking at that, I'm thinking that is what's going to be happening. I'm going to jump you guys back to SAS. One of the big things that's going to be important for us in model diagnostics is the residuals. Do you have big residuals? Do we have some issue where we're going to see later on with homoskedasticity? Well, the residuals are a big help. In proc GLM, to get the residuals and even to predict the values, line 162 does it. Now, line 162, output is the command, add equals info. It's going to create a data set info. R is a shortcut. Now, you see it's in blue. That tells us, oh, this guy wants the residuals of the model. I'm naming the residuals of the model resid. P, it's in blue. It's a name, it's call out for SAS, and P means predicted values. And in my data set, I want the predicted values named with the variable P hat. When I do this, SAS will create, the data set info 19 contains the original data, the 3 variable data, which was cases, design, store, and the 2 additional variables, resid, P hat. So again, if you guys look at the data, let me get back here. If you guys look at the data, so if I go back to Control W, I got a lot of stuff open. I got a lot of stuff open, stuff I was working on. if I go to the info, you see there's the resid, there's the p hat. The p hats are going to be the cell means. In the ANOVA model, the predicted values are the same for every unit within the level of the factor. So design 1, everything's 14.6. Design 2, everything's 13.4. Design 3, 9.5. Design 4, 27.2. So you guys see that. And even if I go back to this and print it out, see that. Now, the residuals sum to 0, right? What we're also going to say is, guys, see, proc means I'm giving you the sum as well as the mean. The residuals sum to 0 within each level too, because it's deviations around the cell mean. The p-hats have no variability within level. They're the estimated means. But again, the residuals sum to 0 within level, sum to 0 total, obviously. And, so mean of 0, sum of 0. That's all we got with the residuals. And again, if you look at it overall, get right there. So again, like we said, the residuals may be good for model diagnostics. Let me show you guys this, right? There's these automatic plots SAS will create for GLM. The one automatic plot we're using is laid by the command plots equal all. So with the plots equal all, I go real quick here, add that in, everything's the same except for this new additional line. LS means design. Plot, mean plot, join CL. LS means stands for least squares mean. It will give us the estimated cell means as well. But this is going to create a plot where we join them with confidence limits. So let me show you what this guy does. So it's the mean plot, but it put confidence bounds around the cell means. That's what that LS means line did, as well as giving me the cell means. Let me go to the top. The plots all created this fit model. Right? So for the fit model, this predictive value, the residuals, in the regression model, you may have done this for the for the homoscedasticity assessment. Now here, really is showing the spread of the residuals. So if something's dramatic, that's where we'd see the violation of Levine's test. The standardized residuals predicted values, again, you may look at these ones bigger than plus or minus 2 as potential outliers. In the regression model, you may have learned about influential observations, the leverage parameters. So the big ones over the threshold may give you a little information about those, as well as the Cook's distance. So Cook's distance with values above these, above the line, there are sometimes what we'll call influential observations. And again, it's just giving you a little bright light. You look at it, see it. We'll talk a little bit about more with some more of the biodiagnostics. This one's really good. This one's showing you the normality of the residuals. We'll show how to do that ourselves, but basically, remember with normality of the residuals, it's whether or not the residuals and the normalized residuals create a line. And what you'll see, and what you guys saw in 512, is they usually snake around the line, and really what you're looking for is really big deviations in in the snake shape, and whether or not there really is a big separation. A lot of times at the end of the scale, you may see a little bit more deviation from the normalized and the observed residuals. This is normality of the residuals, so you're looking for approximately a bell-shaped pattern. So it looks like a little bit of a skew. Whether or not it's significant, we'll get to it in terms of the model diagnostics. And again, a little bit more with the fit. The big ones here that are really of use are this one with the normalized residuals, the Cook's distance, the normality, and the normality there. So we got that. Some of you guys that do some of the mean profile in Gplot, here's some of the Gplot command for you, which is the ones I did with the slide. SGplot has a little bit more better graphics, I think, than the Gplot ones, but that's what you guys see there with the Gplot. But that's what we got there with this, and we saw the residuals there. So again, our deviations, we'll have deviations around the mean, observations around the cell mean, the cell means around the overall mean, and then our total deviation. So mathematically, SAS is, the ANOVA model is divvying up the sums of squares based on the sums of squares of the treatment or the model, and the sum of squares error gives the sum of squares total. Again, we saw the derivation of the test. Again, we're going to live with some of these expected mean squares. So for us, the most important one here is, on average, the expected value of the MSE is the pooled variance. It's the biggest component right there. We looked at the output. Again, if F star is assumed to be distributed this way, when F star is large, we reject the null. Remember the F, the test is one-tailed. More of the output, the R squared. And then we start getting into more of the distribution of the F test. So when F is, when the null is true, F has this derivation. When the alternative is true, the test statistic follows the F distribution, but with this thing called the non-centrality parameter. This non-centrality parameter is going to be really important at the end of this chapter when we talk about power. So what basically happens is, again, if the F star, the test is less than the F value, so p-value bigger than 0.05 or greater than or equal to 0.5, we conclude HO is not the right word. We do not reject HO. Then F star is bigger. We reject HO and conclude H1. So type 1 error is controlled above. Type 2 error, we really get to the sample size. So for us, when we start looking at things with the decision, remember we got the type 1 error, the type 2 error, which is linked to power, and then we got our correct decisions. The non-centrality parameter really looks at the probability we're correctly rejecting the null. The red is the PDF for the central F. The blue is the PDF for the non-central F. And what you guys can see is when we had the non-centrality parameter, the bigger this value is, the bigger we will correctly reject a false null. So that really becomes what we get in there. And that's going to end part 1 of the video. And we'll begin with part 2 of chapter 16, picking up with the factor effect model and take that through to power. So thank you for part 1 of chapter 16, and we'll look at part 2 of chapter 16 next. Thank you.